Okay, so back to here. Um, I already tried to show you how come when we do derivative, a gradient derivative, how come the second term become this? Okay, so the explanation is right here. If you write down every component inside this dot product, you can see when we do, this is a gradient operation. It's a derivative against every variable. So this is partial derivative against x1. So only the first term has x1. So the coefficient is remaining. The rest has no x1. And if we continue and operate the partial derivative against xn, only this coefficient is remaining. So if you check every component right here, you will see, oh, it's actually the gradient vector. So that's why a derivative of this, if we operate a gradient operation of this one, we have the result is actually this portion. Okay? Okay, good. Let's continue on this one. This is more complicated because there is one x term here, another x term here. Okay, so we can try the same trick. But I'm gonna save you some time. Do I save you some time? Let me think about it. So I know the answer is actually plus. Let me think about how I want to write this. I should write this. I know this is the answer. If we apply the gradient operation, this is the gradient operation. And let me think about how do I explain this. So we wish this becomes 0. So we wish this is 0. So the solution has to satisfy this equation so that my first order derivative of my Taylor expansion becomes 0. But I didn't show you why this is the answer. Okay, let me show you on the next page because it's quite complicated. Copy. Okay, paste. Get rid of some portion. Okay, so we want to show something. The gradient operation of this whole chunk. So why this equals to this? So again, let's work on the first term. Before I work on the first term, you need to know this whole thing, if you expand it, if you expand this, you will actually have 1/2 x, not a vector anymore, x1 minus x10 times Let me think about it. It's very complex. Partial, or let me write down H11. That's easier, because our Hessian matrix is n by n. Let me call the first one H11, second one H12. So Hij basically is second order derivative of x partial xi and partial xj. And of course, over here we plug in the expansion point. So if I use Hij to represent the term inside Hessian matrix, that's easier for me. So over here I should have H11 times x1 minus x10 plus H12 times x2 minus x20 dot 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 until we have H1n times xn minus xn0. So this is only the first one. Okay, and then second one, I'm gonna use dot dot dot. And what? 1/2. The last one, x n, hold on. Yes, correct. So last one is xn minus xn0 times what? This time I'm doing the last one, so the last one should do with the last one on the right. So the last one on the right should be hn1 times x1 minus x10 plus hn2, and do this, and plus dot 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 hn xn minus xn0. So this is the whole thing of this term, everything. And then I would like to apply a gradient operation. Okay, but to make it easier, let's work on the first one, the partial derivative against x1. Let's look at that. So in the end, you need to find where are the x1. Here's x1, here's another one, here's x1. Okay, so these are the x1. So these are the x1. So what you will get at the end, basically, you should have so let's work on this one. You should have, because this is a second order, so you will have 2 times 1/2 x1 minus x10 times the coefficient h11. Okay, so this is this guy, the derivative of this guy. Okay, how about the other one? The other one, you should have 1/2 xn minus xm comma 0 times hn1. So you should have this one. So this is first derivative. Okay. And what we had earlier is this. This should give you hatred. Oh, I'm sorry. I should have all of them. Every line has a x1. Every line has a x1. So let me cross out. So this is the first huge term, first term. I should have a second term, and then the nth term is from here. So that gives me 1/2 xn minus xn times hn1. That gives me that. Okay, so this should be my partial, should be my derivative against x1. So let's check if I have this. Copy, paste. If I have this, but I get rid of this. Okay. So let's check what's the first term. The first term should be Hessian matrix, so H11 times x1 minus x 0, 1, 0, and then H12 times x2 minus x2, 0, until we have H1n times xn minus xn0. So this one is this one, but this one is not yet. This is not yet this one. I have a missing term. I have a missing term over where? It's right here. It's right here. Right here. Because I missed this one times this one. So there is a bunch of equations in the first over here that I didn't wrote right here. So let me go back. So let's work on, let me change the color. Let me work on this portion, because they also multiply the coefficient in the front. So there are missing terms. So the missing terms, the first one will be 1/2 H12 times H2 minus x2, 0, until the last one, H1n times xn minus xn, 0. So from here you can see this one and this one together, they're actually this one. But you will see something strange. This is hn1, but this is h1n. They are different. So there is actually one assumption. This derivation only works if Hessian matrix is symmetric. It's a symmetric matrix. So our Hessian matrix. So this is telling you that this one and this one, they are the same. This one and this one, they are the same. Symmetric. So this is actually a symmetric matrix. So if your Hessian is not symmetric, it doesn't work. Okay? So when your Hessian matrix is symmetric, over here, hn1 and h1n is the same. So at the end, you can sum them together. That's how you get this term. So from comparing, we know this is correct. This is correct. Okay, so you can, if you are interested, when you go home, you can try to do this by yourself. Okay, but I know it's a mess on the screen, and maybe you cannot ask me questions right now. So you probably need to go back and try it yourself. Okay, now we know, we just show the derivative of the last part is this one. We just show. So now we can use this. Copy. Sorry. Paste. Now we can use this, and we don't need those. We can use this. So let's rewrite. So basically, x equals to what? X equals to x0 minus, oh, I need to do something, sorry. Before we do that, we need to, let's do it slowly. Let's do it slowly. So Hessian matrix, dot product, x minus x0 equals to minus gradient f, x0. Okay, so in order to continue, I need to operate inverse. So what? Inverse of Hessian. So this is minus inverse of Hessian. And dot product, of course. So at the end, you have the Newton's method equation. Inverse. Okay? So that's an idea. So in iterations, for iterations, basically, x k plus 1 equals to x k minus Hessian inverse, plug in xk, dot product, gradient f, xk. So this is the equation for Newton's method. And let's compare. Compare to 1D Newton. We have xk plus 1 equals to xk minus f prime xk over x double prime sk. Okay, this is the for 1D Newton. So what's the difference? Difference is right here. Because in matrix, you cannot put a matrix at the bottom. You cannot do direct derivative, the divide. You cannot just divide by the matrix, right? So in matrix, when you do dividing, what do? You do an inverse. Okay, so this is trying to help you to memorize this. Okay, so how does the entire flow chart look like? So let me remind you about the flow chart, and also for your reference. Okay, so flow chart of multi-dimensional Newton's method. Okay, so initially you have a gas. So when k equals to 0, you have, this is initial gas. and k equals to 0. So what's the first operation you need? You need to calculate gradient f at xk, and also your Hessian matrix at xk. Okay? Then what's next? Newton's method tell you xk plus 1 equals to xk minus Hessian matrix times gradient. Oops. Okay? And what's next? Convergence check. If the answer is yes, you reach optimal, then your optimal solution is your last solution. If no, if not yet converge, k equals to k plus 1, and then go back again. So this is the flow chart. Okay, just like 1D, but over here everything is in a vector form. Okay, but how about the convergence check? One kind, of course, you still can compare the function value and the previous function value when the difference between function values are small enough. Or you can compare the difference between points. But now we have vectors. The points, we have multi-dimension. We have a vector of points, a vector of point, vector of variables. So how do we compare the previous one and the new one? How do we compare? We can calculate the norm. This is norm. So norm is like a length of vector. And what is this? This is like an error vector or difference vector. So we are checking the length of this difference vector, and we want to stop when this norm is small enough. So you can either say maybe the function value is close enough, or you can say, oh, the distance between points is small enough, or you can say when the iteration number, or I should say reaching, or I should just say k larger than max iteration number. So let's say a problem needs 10 iterations to converge, but you don't have the budget, you don't have the time, you can only do 5 times. So you can say, let's just stop at 5. Okay? So those are the possible check that you can do. Okay, so I think now it's time for me to show you an example, a very simple one, and I tell you the homework. So example. So if I want to minimize f equals to x1 squared plus 10x2 squared. Let's say, yeah. How about let's do minus x1 and plus 5. Okay, something like that. Okay. So let me do an initial guess. Let's say 2, 2. I don't know what the answer is. Of course, I can try to eyeball it and then realize, but I'm not going to do it. Just solve. Now, what does the gradient look like? 2x1 minus 1, 20x2, right? What does Hessian look like? 2, 0, 0, 20. Okay? What does the inverse of Hessian look like? 1/2, 0, 0, 1 over 20. This is the inverse. Okay? I chose this problem because I can easily know the Hessian. Okay? There is no off-diagonal terms. The off-diagonal is 0, so it's a very easy problem. So if I say there's a plus x1, x2 here, then I will have off diagonal terms in Hessian. Then what happened? The inverse is a harder one. You need to follow the procedure of getting inverse. Okay, so that's why I'm not consider this kind of we call coupling terms. Coupling. In this example, I'm not working on coupling terms. No coupling. Okay, so let me continue. Next, Newton's method tell me this equals to x0 minus Hessian inverse times gradient f. Of course, using 0. I'm going to skip some of the, just make it simple, okay? So here I should use 2, 2 minus 1/2, 0, 0, 1 over 20 times 2 plug in this guy. So I will have 4 minus 1, 40. So in the end, I have 2, 2 minus 3 over 2, 2. So I will have 1/2 and 0. Okay, I don't know if that's the answer. Let me check. The difference between x1 and x0 is the norm of 1/2 0 minus 2, 2. So basically it's the norm of this vector. And how do you calculate this? Basically 4 over 9 plus 4 and blah blah blah. It's larger than 10 to the power of -3. Okay, I'm not going to solve it. So not yet converge. So I move on. K equals to k plus 1. So now k equals to 1. At the beginning, k equals to 0. Okay? So next what I do is I directly use Newton's equation x2 and I started to plug in. The previous solution is 1/2 and 0 minus the inverse Hessian. And now the key is to plug in this guy to the gradient now. So 2 times 1/2 minus 1, 20 times 0. And you know what's happening. This is basically 0, 0. So of course you get the exactly same solution. So when you do the check, the second solution minus the first solution, of course it's 0 because there's no difference. This one and this one is the same. So it's of course smaller than 10 to the power of negative 3. So converged. My optimal solution is my last solution, which is 1/2 and 0. This is how you do it. Okay? So let me give you a homework. Homework 2. First, homework 2-1. I'm going to give you 2 homeworks. The first problem. Minimize f, but over here f of x equals to what? x1 square, let's try plus 5x2 square, and let's try 2x3 square. So it's a third order problem. Okay, let's try, I mean not third order, the 3-dimensional problem, 3 variables. Let's try that. And over here, let's say I do a plus 2x1 minus 6x2 plus 8x3 minus 20. Okay, let's try to solve it. And I can guarantee you Newton's method can solve in 2 iterations. So you just need to take some time to handle the inverse. Actually, in this one, the inverse is also very simple. Never mind. Let's just work on that. And how about the initial start? Just randomly pick. Okay? So please pick on your own. Don't copy other people's initial point. Okay? Just randomly pick some point. Please do not copy. Just do your own homework so that you learn. Okay? And of course, this will be Newton's method is a very important method. This will be included in the first exam. So I wish you use this week to practice. Okay? Any questions? Raise your hand. Okay, let's do a 5-minute break. I will give you some time to take a rest, to think about the whole process, and make sure you understand. So 5 minutes. We come back in 5 minutes.